Okay, we'll record. Okay. Bueno. Okay, remember, you don't put that on. Okay. First topic we're going to talk about is significant digits. Sometimes it's called significant figures as well. Significant digits are all the known digits plus the first, we call it estimated, plus the first estimated digit. And I'll go ahead and say estimated, yeah. We're guessing. We're guessing here. Now, the concept of significant digits is pretty easy to understand. Okay? You're going to take some measurements in here. You do in all areas of science. And then you're going to do something with those numbers. You're going to multiply them, divide them, add them, subtract them, whatever. And you're going to get an answer. But your answer can't be more accurate than the numbers that were used to generate it. That's the concept of significant digits. Any number that you generate using other numbers, that answer has to reflect the accuracy of the numbers used to create it. It's that whole chain, weak link thing, right? So what we have to do is, we have to first learn how to determine how many significant digits a particular number has. We need to know how to round our answers to the correct number of significant digits. Okay, so we're going to begin by taking some measurements. And I arbitrarily just take this little box here. When you take a measurement in here, and you're going to have to do it a number of different times, you're obligated to record your data to the maximum accuracy allowed by the instrument. And instruments have varying degrees of accuracy, and therefore varying degrees of reliability. So I look at this, and I see it's got marks at 10, 20, 30, 40 centimeters. In between the 10 centimeters, I see 10 equal areas, little marks. And then even within those, I see 10 marks. So this thing will measure down to, the instrument itself, down to 1/10 of a centimeter. That's known. Okay? Significant digits are all the known. If it measures down to the 1/10 of a centimeter, then our first guessed at digit will be the hundreds place. Right? So let's check it out. I'm going to take our measurement here, and using this particular instrument to measure, the only thing I can say is that this is greater than 24.8, but less than 24.9. That's what this instrument tells me. So, using that, using that particular instrument, the only thing I know is that the length of that box of gloves is greater than 24.8, but less than 24.9. So I'll take another look at it. And it looks to me like it is just, it's more than halfway. In fact, it's really close to the 24.9. So it's greater than halfway. Centimeters. Known. Guess. Now, different people looking at that same meter stick will have a different number here in the back. Someone could say it's 0.9, some could say it's 7. I think everybody, though, based on what I saw, everybody would say it's greater than halfway. So your number is going to be 5 or greater. Okay. Then we take another instrument. It's like this. Now this one only has marks at 10, 20, 30, 40, 50, 60. The other ones are there, I just covered them with tape. Right? So we're going to measure this thing again using our new instrument. And we're going to say the only thing I can tell from this is that it's greater than 20 but less than 30. Right? So using our second instrument, we see it's greater than 20 centimeters but less than 30. So we take a guess. Right? It almost looks like it's right in the middle, right? Pretty close. We know it's 24 because we already wrote those up there, right? So we take a guess on here, and some people might guess 25, some people might guess 24. Let's guess 24. Known. Yes. Right? So your data, when you write your data down, you're obligated to take it one more than the smallest measurement on your device. Okay? You don't arbitrarily cut digits off. You have to record it to the maximum. We'll deal with rounding and cutting the digits off later, but when you're actually acquiring the data, you're obligated to record it to the maximum accuracy allowed by the instrument. Okay? Everybody good? Okay, so if we look at these, we see that there's some reliability in our numbers, right? We don't know much about the reliability of this, or this, but we do know that the reliability of the last one's in question because we actually guessed that. So we want to know, how do we determine what digits are significant? How many of these digits do we need to consider when we're doing our mathematical operations? And we use the Atlantic Pacific method. I know this is a slight variation from the method that's presented in the text. The more ways you hear it, see it, better off you're going to understand it. Has anybody ever heard of this? Atlantic Pacific? Okay, good. Well, the Atlantic Pacific method has one design flaw. And that is, you need to know where the Atlantic and Pacific Ocean is relative to where we are right now. We're in Southern California, right? So, the Pacific Ocean is on our west, and the Atlantic is to our east, right? We know. This method won't work in the Far East because it's reversed. We're going to be dealing with two types of numbers in here. We're going to be dealing with those that contain decimals and those that do not. Very rarely in any area of science will you represent a number in fraction form. It's either going to have a decimal in it or it's not. And that's really what the P and the A stand for. It stands for decimal point present. What do you think the A stands for? Yeah. Everybody with me so far? Okay. So let's take a look. When you're determining significant figures or significant digits, first of all non-zero numbers are significant. They always are. The zeros are the ones that are going to create a problem. Whether or not these are decimal placeholders, whether they're trailing zeros, they have all sorts of names for these types of zeros. But it will be the zeros that cause the confusion. This particular method does not differentiate between zeros and non-zero numbers. Okay? So we're just going to start with an example. 39.7. Okay? We could look at that and we could say these are non-zero numbers. So they're all significant. So you count it up. 3. Okay? But is there a decimal present? Yes. If the decimal is present, we start from the Pacific and we move toward the Atlantic. We don't start counting until we hit a non-zero number. But once we hit that non-zero number, we count all the way to the end, zeros or not. So, decimal point present, there's our first non-zero number, we start counting. 1, 2, 3. We count all the way to the end, whether they're zeros or not. How many?
5.
5, I got 8, 12. Decimal point present? Yep. Decimal point present, we start at the Pacific, we start moving toward the Atlantic. We do not start counting till we hit a non-zero number. But once we hit the non-zero number, we count all the way to the end, zeros or not. 1, 2, 3, 4, 5. This number has 5 significant digits. Everybody see that? Well, that one. 2. You sure? Anybody else? 2? Again, decimal point present? No. Now the decimal point's absent, so we start from the Atlantic and we move toward the Pacific. But we follow our same protocol. We do not start counting until we hit a non-zero number. But once we hit it, we count all the way to the end, zeros or not. 2. Now how many?
4.
Now it's got 4, huh? There's a difference. There's a difference, okay? There's a difference between having the decimal point there and not having the decimal point. When determining how many significant digits a number has, you're going to count left to right or right to left. Right? And in this particular instance, when you have decimal points, you count left to right. When you don't have a decimal point, you count right to left. But in either case, you don't start counting until you hit a non-zero number. And once you hit that non-zero number, you count all the way to the end, zeros or not. Okay? It's a quick, easy method for determining how many significant digits a particular number has. But that's the only question it can answer. The only thing that Atlantic and Pacific method is good for is to say or answer how many significant digits in this number. Okay? Now, why do we need to do that? Everybody good with this? Everybody good with determining how many? So you're going to have to do that on the homework, you're going to have it on quizzes, the whole thing. So I have a number here. And I picked this number because I wanted a different digit in every place so that when I ask you, what is the second significant digit? What's your answer? The second significant digit. 4? Why 4?
Because there's no decimal.
Why?
There's no decimal.
What question did I just ask you?
Why is it 4?
No, what is the second digit, right? And what did you use to answer it?
Oh, the Atlantic and Pacific method?
You did, but that wasn't the right. Atlantic Pacific can only be used to answer how many digits. It doesn't tell you what is. You don't say, well, oh, there's no decimal present, so I'm going this way, and this is the second digit. Okay? Atlantic Pacific doesn't serve that purpose. It's only good to tell you how many. All right? Now, if we look at our earlier examples where we took our measurements, right? If we were to look at both of these measurements, what number, what digit are we the most confident in? Which one are we the most confident with? The 2, the 20, right? Not necessarily a 24, because in this particular example, someone could have easily guessed 25. This is our guess stat, right? But both of them contain the 20. So we're pretty confident in the 20, right? And then we lose confidence as we go left to right, until eventually we get a number that we actually guessed at, which again, we have no confidence. So when you're determining what is the first digit, what is the second digit, always start from the left. Always, always, always. And it doesn't matter second significant digit, second significant digit. Always start from the left. Okay? Everybody good with that? There's a difference between how many significant digits in a number and what is the first, second, third, fourth. And we need to know that because we're going to round based on the number of significant digits in the data that was used to generate our answers. Okay? Everybody good? Sure? Okay. So why are we doing all this? What's the value? Well, we're going to have to do some type of mathematical manipulation in here. When we do our experiments and we take our exams and we do our calculations, there's a reason why. There's an end result. There's an answer. Right? So we have to make sure that our answer properly reflects the accuracy of all the information that created it. So when we multiply and divide, SF is significant figures, significant digits. I go back and forth on that. So if we were to take say that we had this mathematical operation. Say that we want to multiply these numbers together. Okay? And I have 1.2 times 3.7 times 29.86. I got this number. That's the number I get, my calculator. Okay? Look at tens, hundreds, thousands, 10,000s, 100,000s, millions. Our answer has a decimal place to the millions. It's pretty darn accurate, right? Obviously, we cannot report this answer as the product of these three numbers, the multiplication of those three numbers. So we have to round this number to reflect the accuracy of these numbers. So what we do is we have to individually determine how many significant digits, that means Atlantic Pacific, right? How many significant digits in each one of these. Then once we do that, we round this one to the least number of significant digits, the one with the lowest. So, how many significant digits? 2. How many? 3. How many? 3. What's the lowest number? 2. We have to round this to the second significant digit, which is, what's the second digit? 7 is the second digit. What's next door? 5, which means we round up. 3.8. We would have to report this answer as 3.8. Everybody see? So, from now on, you shouldn't even ask. Yes, all of your answers have to be reported to the correct number of digits. Whether you're in lab, whether you're doing homework, whether you're on exams, quizzes, it doesn't matter. So you don't even need to ask that question, right? Everything has to be reported to the correct number of significant digits from now on. And it would still be okay if we had, if we had another number that only had 2. It doesn't matter. It doesn't have to be just one number, right? They can all have the same number of significant digits. If they were all 2, 2, and 2, you would still round it to 2. Okay. What about adding and subtracting? Adding and subtracting. When we add and subtract, we don't use significant digits. What do they tell you in math class when you're adding numbers with decimals? Line them up. Don't they say line them up? So if we have some numbers with decimals, say we have some numbers with decimals. I just made those up. Let's make this 3. 3.82. There's 2 ways you can look at it. Okay? The first one is to look at what's the least accurate piece of data here right now. You look at this and you say, this has a hundreds place, this has a tens place, this has a hundreds place. The tens place. So the last digit in your answer is going to be the tens place. That's one way to look at it. Okay, you look at the number that has the least accurate number of decimal places. Another way is to line up the decimals. I'm a little partial to lining up the decimals because a very effective way to learn something is to associate it with something that you already know, i.e. line up the decimals, and then take it just a little further. So we're at 3.82, right? Now, when you line up the decimals, you're going to see a smallest decimal value that's common to all of your numbers. Okay? We have the ones that are common. We have the tenths place that are common, and then hundreds. This one doesn't have hundreds. So the smallest decimal value that's common to all of our numbers is the tenths place. So I'll box it. And I'll say, okay, whatever's in that box, that's the last digit in my answer. And I'll round it based on whatever number is right here. So I'll do my adding. 18, carry the 1. What do I have here? 10, 13. Right? We don't need a calculator, right? So, 8, next door is a 3. I will report 13.8. Okay? Notice if you mess up. If you make a mistake and you say 3 significant digits, 2 significant digits, 3 significant digits, and you say, gotta round it to 2, 8 next door, 14. And on your multiple choice exam, guess what answer 14 is going to be? A. It's going to be A. And you're going to sit there and you're going to say, I got that one right. Right? With a little star next to it. Because you do that with all the ones you got right, 100%. So you can get some measure of how you do on the exam, right? You know I got that one right. No problem. And you get it wrong and you come up to me all mad and you say, I got this right because it's 2 significant digits. And I say, whoa, 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 whoa. They're adding. And you say, ah. Oh. Be careful. Be careful. Adding and subtracting, don't use significant digits to round the number. Line up the decimals, whichever column, the last column on the right, which is common to all of them, that's going to be the last one in your answer. Okay? Be careful. I promise you on the exam, if you use significant digits on adding and subtracting, that answer is going to be one of your choices. It will be. Okay? So be careful. Just remember, add, subtract, no significant digits. Multiplication and division, significant digits. Everybody good? Okay. So we're rounding. We're talking about rounding. Rounding numbers based on, in some cases, significant digits, based in some cases not. 4,000. Please round that to the second significant digit. What's the answer? 40? You give me $4,000. I'm going to round it and give it back to you. Give me $4 grand, I'll give you 40. What is it? How do we round this number to 2 significant digits? Yeah, I know what you're saying. Yeah, that's what we're going to do. But for now, if we look at this number, and this particular number, how many significant digits does it have? 1. Atlantic Pacific, right? How much does a truck weigh? About 4,000 pounds. Because remember, if there's one significant digit, and significant digits are all known digits plus the first guessed at, then if you have one significant digit, you guessed at it, right? It's guessed at. How much did your truck weigh? About 4,000 pounds. How many does it have now? Now it's got 4. Now, no, I put my truck on a scale, and it weighs 4,000 pounds. See the difference? But it appears that this number can only be represented in either one significant digit, which we saw first, or 4. So how do we do it in 2? Because it can be represented in 2. How do we do it?
4.0 times 10 to the third.
Yes, that's right. What is that called? Scientific notation. Sometimes you run into numbers that you have to put into scientific notation in order to show them correctly rounded to the appropriate significant digits. This is one of those times. Scientific notation is simply an alternative method to represent numbers. And in order to have a number correctly written in scientific notation, you have to have a couple of things. I'm going to just write one in. First of all, you have to have a decimal value. Now, it doesn't mean that the number has to have necessarily a decimal. It could be represented like this, 3. We have to have a number that's greater than 1, but less than 10. This number has to be greater than 1, but less than 10. It could actually be equal to 1, greater than or equal to 1, but it has to be less than 10. In other words, you can only have one decimal place to the left of your decimal. Only one. Okay? The second is you have to have a base 10. You have to have 10 to the certain power. If you fulfill both of these requirements, you have a number correctly written in scientific notation. Okay? So how do we do that? Well, first of all, we can take any number and we can multiply it times 10 to the 0, because what's anything raised to the 0 power? 1, right? Anything raised to the 0 power equals 1. 6 to the 0, 5 to the 0, 10 to the 0. Anything raised to the 0 power is equal to 1. Now, why do we do that? We do that because we just fulfilled one of the conditions for scientific notation. We've given ourselves a power of 10. Now all I have to do is get the value of my number to have a single decimal place to the left by simply moving the decimal point. And I'm going to move the decimal point to the left, or I'm going to move it to the right. I have to. In this case, I'm moving my decimal point 1, 2, 3 places. 3 places to the left. When you move your decimal point to the left, you go positive on your exponent. So, what's positive from 0? 3 places plus 3. Every time you move this decimal point, you change the value of your number. It's called an order of magnitude. So I can write this. See what I did? Every time you move that decimal, it results in a full order of magnitude, either in the positive direction or the negative direction. From 0. 0 is our starting point. Okay? The beauty of numbers written in scientific notation is you don't have to worry with all that Atlantic, Pacific, or any of that other stuff. When you see a number written in scientific notation, you just count all the digits. Everything is significant when the number is written in scientific notation, when it's correctly written in scientific notation. So, when you're looking at the original 4,000, you can show 4,000 a number of different ways. All of these values equal 4,000 because they're all 4 times 10 to the third. What's 10 to the third? 10 times 10 times 10. 10 times 10 is 100, times 10 is 1,000. 4 times 1,000 is 4,000. So they all have the same value. It's the reliability that's attached to each representation that differentiates them. So this is only one significant digit, which would be equivalent to that. This is 3 significant digits, which would look like sorry, it's 4. It's 4 significant digits, 1, 2, 3, 4. Okay? Here it is to 3 significant digits, here it is to 2 significant digits. So in some cases, you're, unfortunately, it's unfortunate, but in some cases, you're absolutely obligated to represent the number in scientific notation because that's the only way you can represent that particular number to the appropriate number of significant digits. Okay, it's not real common. Okay, it's not real common, but it's not extremely rare either. You will run into it once in a while. Okay? Let's take a look at one going the other way. Take a look at this one. Who's that? Yeah? What is that one? In significant digits.
4.21 times, 10 to the negative 4.
And then negative 4. I'm moving my decimal again, and you could set this up the same way, okay? Times 10 to the 0 because that's basically 1, right? And you start moving your decimal. So now we got 0.00421 times 10 to the negative 1. When we move our decimal point to the right, we go negative. So in this case, let's back up. We're going to go 1, 2, 3, 4. Notice I moved my decimal to a point where I had just a single digit to the left of the decimal. Kept track of how many times I moved it. I'm moving from 0 and then negative 4. Okay? Everybody good? All right, let's convert a couple more. Let's round that one to 3 significant digits. I want your answer in scientific notation. What is it?
1.75 times 10 to the second.
Times 10 to the what?
To the second. So we do the digits first time around.
Move to 4 places, right?
Right.
Times 10 to the 4. You see that? Did you guys get that? Got it? What if we wanted to convert that number right there into a decimal form? What would we do? You do kind of the opposite of what we did to create it, right? If we're looking at this, the way I remember it is I say, well, this is a positive 4, right? And I remember my number line. That's positive, that's negative, right? So this is a positive 4, so I have to have 4 places in the positive direction of my number, which is that way. So I would go 1, then when I'm moving my decimal, there's my first one, there's my second one, third one, fourth one. You need 4 places in the positive direction. So you just move this 4 places. 1, 2, 3, 4. Now you don't put the decimal point in there, do you? Why wouldn't you put the decimal point in there? Here's our original number. Right? Why wouldn't I do this?
That makes it exact and it's not guessed.
Doesn't necessarily make it exact, because it could still be a measured number depending on what the units were. But how many significant digits do I make if I put a decimal point in here? How many does this have? 3. So you don't change the accuracy, i.e. the number of significant digits, by converting a number between scientific notation and decimal form. That doesn't change the accuracy, all right? All you're doing in scientific notation is representing the number using an alternative form. That's all. That's all you're doing. You're not making the number more accurate, less accurate, whatever. If you round it, you are. I mean, this was our number, right? But this number obviously was far too accurate given the numbers that were used to generate it, because I wanted it to the 3rd significant digit. So when we rounded it, we have to maintain the same number of significant digits when we're converting between scientific notation and decimal. Same thing with, with a negative. Okay? We think of our number line, we want to convert to a decimal, we're going in the negative direction. 1, 2, 3. Now in this case, we do require the decimal, but it still doesn't change the number of significant digits. It's 2 in both cases. Everybody see that? Now generally, on most exams, you'll be free to express the answer in either decimal form or scientific notation, whatever you feel most comfortable with. But unfortunately, on multiple choice exams, you may come up with an answer, and then you go to look for your choices, and it's not there. Okay? Only the decimal value's there. Or sometimes they might explicitly call for the answer to be represented in scientific notation. Okay, we do that from time to time. All right? Everybody cool? You sure?
Yes.
I don't know if I believe you yet. Okay.
Just a quick question.
Yep.
So when we're in the positives, we lose our decimal, but when we're in the negatives, we keep that decimal.
Yeah, well, just remember that once you convert a number into scientific notation or convert it into decimal, you're going to be given one, right? They give it scientific notation, and you want the number in decimal form. When you convert it, just make sure the significant digits match on both numbers. But yes, that's generally going to be the rule. When you're moving the decimal point to the right, you're not going to show it. When you're moving it to the left, you do. But in either case, those zeros, those positions that result from moving the decimals are not significant. Because adding zeros here it's not significant unless there's a decimal.
Yeah.
I think your general rule is, I started out here, here's my answer, how many significant digits? How many significant digits? If they match, you're good. And you should always be, the same value, obviously. You don't want to do 4,040. If you say, I'm rounding 4,000, I get 40, you made a mistake. Go back and find it. You got to be in at least, the same order of magnitude when you're rounding.
So in the book, there's one that's 4.0100 times 10 to the 6th.
So it's,
Like that, in that form, it's 5 significant numbers.
what is it? 4 point?
0.100
Yes.
times 10 to the 6th.
Yeah. I'm 10 to the 6.
And it says it's 5 significant numbers there, but if you were to convert it, it wouldn't.
Can't.
But you can
No way you
convert
can do it. Yeah. There's no way you can show this to the correct number of significant digits. Because you'd have to move this 6 places. 1, 2, 3, 4, 5, 6. That's going to require you to put more zeros on there, and there's no way you can show this to 5 significant digits.
So you wouldn't convert it then?
No, you can't.
Okay.
Not correctly.
Thank you.
And your tip off that you can't do that is when there's zeros in here. When there's zeros in your scientific notation number, when it ends in zeros like this, there's a reason why they did that. And that's because that's the only way they can show that number to the appropriate number of significant digits. Okay. Now, the next topic is dimensional analysis. And I think this is one of the more important concepts that you'll learn in this class. It's not necessarily a chemistry concept, but it's still one of the more important concepts. And if you can master this particular technique and skill, you're going to use it in physics, you're going to use it in a bunch of other areas of science, you're going to use it in math. It's going to have applications in a more diverse part of your life than just chemistry class. And in order to use dimensional analysis, I'm just going to start with an example. Right? We're going to convert, let's convert 1.27 years into seconds. Let's convert 1.27 years into seconds. Anybody know that direct conversion? Yeah, me neither. Me neither. I don't know how many seconds there are in a year. Most people don't. So what we're going to do is we're going to start by taking our given information and making a fraction out of it. And we know from math that you can take any number and make it a fraction by simply putting it over 1. Right? They also told me many moons ago when I went to school that anything over itself is equal to 1. They still telling you that? Still telling you that? Anything over itself? Does that mean 1 over 10 is equal to 1? I mean, conceptually, you can't argue with it, right? I mean, they didn't say any number over itself is equal to 1. They said anything over itself is equal to 1. 10 over 10 should be equal to 1. Don't try and think about it, right? Don't. Look,
It's philosophy.
pen over pen ain't working. Okay? Don't try and think about it. But we can't argue with it. right? We can't argue because they have told us in the past anything over itself is equal to 1. We're going to use that. And we're going to say, look, if I can get any unit over itself, then I can cancel those units out because anything over itself is equal to 1. So I'm starting with my years, and I have no idea what I'm going to do or how I'm going to do it. The only thing I know is that years is in the numerator in my given information. So it has to be in the denominator in my next fraction. That way it cancels out. Now let's think about some of the conversions for a year. What could we use? Days, 365 days in a year. We could use months, there's 12 months in a year. We could use weeks. Okay, let's use days, because that was first. You could use the other ones. Let's say days. How many days are there? Don't say anything about no leap year. 365 days in 1 year. I got year in the top, year in the bottom. I'm canceling. Don't know what I'm going to do next, but I do know I got to have days here. Where can I take days to?
Hours.
Hours? That's a good one. What is that conversion?
24 hours is 1 day.
24 goes with the hours, 1 goes with the day. That's our conversion. I got day in the top, day in the bottom, done. Next, don't know. But I do know I'm going to hours in the bottom because I have to. Where am I going to take hours to? Minutes. What is that conversion? 60 and 1. If I stop right now, all of my units are canceled and gone except minutes. Unfortunately, it's not what I'm asked for, but I'm getting close, right? My last one, I want to have minutes. What goes in top? 60 seconds, right? We're getting the hang of this. Seconds. Minutes are gone. No problem. I started out with years. I converted years into days, days into hours, hours into minutes, minutes into seconds. See the little zigzag pattern that's developing here? Let's see what our answer is. Oh, there's a lot of them. Whole lot of seconds. Guess that's right. Let me try it again. Yep. There it is. Where do you think that answer is going to be on your exam? That's not going to be there, huh? Because we can't report that answer. Right? What do we have to do with that answer? Sig figs. We have to round. Sig figs. How many? 3?
2.
2?
Oh no.
1?
There's 1.
What do you say?
1.
1? Nothing.
It's 1.
1? Why is it 1?
Because 60. 60 is 1 second.
Right. Right. First of all, you're the first class that's ever noticed that. Right? Unfortunately, it's wrong. But when you look at this multiplication and division, remember when we multiply and divide, We have to look at all of the numbers, we assign significant digits to the number, and then whatever the lowest number of significant digits is, we round our answer to it. Well, correctly, up here in the front, they're saying, hey, this only got one significant digit. This only has one. This has one. 1, 2, 3, 1, 3, 1. 1 is the lowest number. I should round my answer to 1. But here's our issue. What are these? What is this called? What's this called? What do we call that? What did we do with it? What do we use it for? What do we use it for?
We divide and multiply to get our conversions.
Conversion is the key word. That's a conversion factor. How do you know it's a conversion factor? It's got a different unit in the top than it does in the bottom. Okay? Conversion factors are numbers that have different units in the numerator and the denominator. And their whole purpose for existing, the only use they have for us, is to convert between those units. That's all we use them for. That's all we ever use them for. You can't use this conversion factor to calculate the number of gallons in 400 ounces. You have to use a different conversion factor for that. Okay? So, when we have a conversion factor like 60 seconds in 1 minute, is that really the conversion factor? Or have we simplified that number just so we can, just for clarity? Couldn't I say this is 60.000000000000 seconds in 1.000000000000 minutes? Couldn't I say that? Yeah, I can. Conversion factors, and as a matter of convenience for their use, they're simplified. We can take them out as many digits as we want. Why would I write something like that? Still the same value, but it's clearly more accurate. It's got way more significant digits than this number. So, conversion factors are conveniently simplified so that we can use them. And therefore, they will never be the number that has the lowest number of significant digits, because we can put as many as we want on them. So we simply don't consider it. It's the bottom line. Whenever you see a conversion factor, we understand that this can have as many significant digits as we would like to put on it, and therefore we don't consider it for the number with the least number of significant digits. It's only data. How do we recognize data? How do we recognize it? Why? What's this number is different from all the other ones? Why?
It's a measure of unit.
How many units? How many units on that number at the top? 1. It's just got years on it. See? It's just got years. So when you see a number with a single unit on it, instead of a number that has a numerator and denominator of the units on it, these are the only numbers that can be considered for significant digits. Okay? I usually like to say, look, when you're rounding your answer and you're trying to determine how many significant digits you have, go back to the original problem, because it's something in the problem that's going to tell you the least number of digits, not something you wrote down. It's going to be something that's given to you. So look for the number with the single unit on it, or if there are a bunch of numbers with single units on it, you have to look at the significant digits on each one of them and round it to the one with the lowest number. So, correctly stated, 3. What is this round to 3 significant digits? There's a third one, right? Or you could put that in scientific notation, right? 1, 2, 3, 4, 5, 6, 7. Alternatively, three significant digits, 3. Everybody see that? The beauty of this dimensional analysis in these types of problems, the beauty of them is they all follow the same protocol for solving. There's no tricks to them, okay? You will make them more difficult. You will make certain conversion problems more difficult than other conversion problems. And that will be based solely on the familiarity that you have with the conversion factors. This was pretty straightforward because everybody in the class knows that 1 unit 365 days, 1 day 24 hours. But when you start using conversion factors that you're not familiar with, somehow the problem just becomes much more difficult and you can't solve it. Now, you don't have to memorize any conversion factors because we give you this page, this periodic table, and any conversion factor that you need is right there. Okay? Now, it might not be written in a form that you're really comfortable with, but take a look. We look at one. Let's pick one out. 1 foot, 12 inches. Nice easy one, right? 1 foot equals 12 inches. Now you have a bunch of conversion factors on that sheet, but they're all written in this manner. They're not written like this. They're not written that way because we don't know if you're going to need it in this form or the inverse of that, inverted form. If you have a conversion factor that says 1 foot is 12 inches, the form that that conversion factor takes is dependent on what you're given. Okay? So, the whole reason for the existence of this conversion factor is to convert feet to inches or inches to feet. So if you had something like, calculate the number of feet in 47 inches. You would have 47 inches over 1. We follow our protocol for solving. I know that inches have to be in the bottom in the next one. Wherever the inches go, that's where the 12 goes. What if I had calculate the number of inches in 4.21 feet? I'm stuck on 47. Say 4.2 feet. Now we write our given information down. Again, we follow our protocol. And I say feet are in the top, so feet have to be in the bottom. Inches now on top. Wherever inches goes, 12 goes. This is what I get. So the form that the conversion factor takes is entirely dependent on what you're being asked. Okay? Or what you're given. If you're given inches, then inches go on the bottom. If you're given feet, then feet go on the bottom. Notice these conversion factors don't have the same value. This is 1/12. This is 12 over 1. Okay? Everybody see that? Let's see if I can find one. Okay, let's convert 19.8 pounds to kilograms. Kilograms. Go ahead. Don't freak out, all right? Start with your given information just like we have in the past. Put it over 1. It's going to give you pounds in the numerator. Pounds go in the denominator. Simply go to your reference and see where you can take pounds to. Find something that's suitable. Go ahead and take it to that particular unit. If that unit is not kilograms, take it somewhere and you can get kilograms. You got an answer? Anybody got an answer? What is it?
9 kilograms?
A little more specific? I got 19.8 pounds, right? Don't know really where I'm going, but I gotta have pounds. That is. What do I want to take my pounds to?
Kilograms.
Directly to kilograms, right? And what is that?
1 kilogram. So 2.2 pounds. 2.2.
0.
0.
Okay.
Ooh, okay. So, divide that out, what do we get? 9? Right? 9 kilograms? Is that correct? Is that right? What'd you get? What'd you get? What do we got? 9.00. There's 3 significant digits here, right? You can't lose that accuracy just because you did a conversion, right? Got to keep that accuracy. 9.00, very good. Everybody see that? Okay. Everybody good? And these are more like the ones you're going to see on the exam. Pretty straightforward. You're just going to have a couple of conversion factors. You're not going to see one like we did before, years to seconds, where you have to have 3 or 4 or 5 conversion factors. That's not how it's going to be. It's going to be pretty straightforward, maybe 1, certainly 1, maybe 2 conversion factors. Let's try one that looks a little different. $23 meters per second, 2 miles per hour. Oh, did you get that in the other class?
Yeah.
That's good. No, I'm okay for now. Now this one's a little different, right? This one, you have two conversions to do, so just handle them separately. Just convert, you convert the numerators, miles, or meters to miles, and then convert the denominators, seconds to hours. Nothing's tricky about it. It's just basically two conversion problems in one. How do you know 3,600 seconds? Yeah. Here. Looks good. What? Which part? Just go miles, meters, kilometers, miles. So I would go 60 seconds. Minute, 60 minutes in an hour.
Meters right here, isn't this,
That's mine.
okay, so then
So-
this is mine.
Yeah, so here, kilometers, miles,
So
miles in the
miles has
top.
to be right here, right?
No, miles is what you want. Look at it. Miles, no, stop. You would know that because you'd start going in a circle.
Yeah.
You'd say, where am I gonna take miles? Oh, that's kilometers or feet. And then you'd say, where are feet? Centimeters, or centimeters, to meters. And you're like, wait a minute, I'm going in a circle. Which wouldn't make the math wrong. It just makes, the calculations a bunch more. Anybody got an answer? No, not yet? Make it all one. Make them all one, okay? Okay, we're going to do a couple of conversions. Now, sometimes when you have to do two conversions like this, I like to say, look, if you have 23 over 1 meters over seconds, and then you multiply those, you get 23 meters over 1 second. Now, most of you saw that, but the bottom line is sometimes these are written, with the number here and then the fraction after, and it throws people off. 75 miles per hour, right? You can write that, and you would have to write that like that, okay? Because you'll see it. You'll see it in density problems. You're going to see the number, and then you're going to see the fraction that contains the units. And sometimes it throws you off. But just remember, the number can always be converted to a fraction by putting it over 1. And then you have already your units are in a fraction, so you multiply numerators, multiply denominators, you get it, okay? So if we start here, and I'm writing it in the middle for a reason. I have to do two conversions here, so to keep my sanity, I'm going to convert one in this direction, and I'm going to convert the other in this direction. Just so I don't get my fractions too far away from each other. Even though if you did it in one long single conversion, it's fine. So let's do the meters first. I have meters in the top, so I have to have meters in the bottom. What are some of the possible conversions of the meters? Where do I want to take it?
Kilometer,
Kilometer? Okay. What is that conversion?
1 over 1,000.
1
Kilometer to 1,000.
and 1,000, right? Meters are gone. Right? I'm still not to miles yet. Kilometer, kilometer, to what? Miles. What is that conversion? What is it?
1.61
1.61 what?
kilometers.
Right. 1.61 kilometers in 1 mile. I stop. I'm good. Miles. I'm done. I'm done with my top. All these canceled out. If I stopped right now, I'd have miles per second. Unfortunately, that's not what I'm asked for. I'm asked for miles per hour. So all I have to do is convert my seconds to hours. So you can keep going over here and put seconds in the top. Now this is the first time we've seen this, where we're converting a unit in the denominator. But it doesn't change our protocol. If it's in the bottom here, that means it has to be in the top up here. Okay? Doesn't matter, as long as there's one on the top and the bottom. What is that conversion? Where do we want to go? Seconds.
Minutes.
I go to minutes. What is it?
60 seconds.
60 seconds, 1 minute. Seconds are gone. Now I'm at miles per minute. Someone in the back knew it was 3,600 seconds in an hour, so just put that directly in. Minutes on the top here, so I can cancel. We'll go to hours. 60 minutes, 1 hour. Minutes are gone. What's the only unit I have standing on the top and the bottom? Miles per hour. I'm done. Everything else is canceled out. This has to be right as long as I don't make a mistake putting the numbers in my calculator. So we do the math, and what do we get? I forget. How do you do this one? If you're going to multiply a lot of numbers across, okay, and you have numbers in the top and the numbers in the bottom, I think most people multiply all the numbers in the top, write that number down, multiply all the numbers in the bottom, write that number down, then go back and put the number that they wrote down previously back in the calculator, hit divide, and then put the number they put in the bottom back. Too many places for mistake. Just do what you're told to do in one straight, solid set of keystrokes. I'm not going to divide or multiply by 1 because it doesn't change the answer. So I would go 60 divided by 1, but I'm not going to do it, times 60 times 23 divided by 1,000 divided by 1.61. See how that works? You don't go 60 times 60 times 23 divided by 1,000 times 1.61. If you do that, it's going to divide that answer by 1,000, then it's going to multiply it by that number, unless you put parentheses. But don't do it. If it's on the bottom, precede it with a divide key. If it's on the top, precede it with multiplication. Okay? One set of solid keystrokes, minimizing error. There's still a possibility to make error, I'm not saying that, but at least it minimizes it. I've got 51.42857. 51.42857,143. Miles per hour. Somewhat more accurate, right, than our data. What are we going to round it to? 2. What is the answer there? There's our 2. Now, even though this is a conversion factor, right, it was still given information. So it's really the only piece of information that we have to go by, even though it has a unit in the top and the bottom. Okay, this still could be and is considered a conversion factor, but it was the only information we're given. So we're going to go to 51 miles per hour. Okay? Everybody see that? Okay. How about You see how these are all tackled the same way? You approach them all the same way in terms of converting one unit into another, using units in some cases that are familiar to you, like 60 seconds in a minute, but then some that aren't as familiar to you, 1.61 kilometers in a mile. How about 0.714 grams per cubic centimeter into pounds per cubic foot. Uh-oh. Setback. It's all the same thing. Don't be thrown off by that cubic thing. If you have a conversion of centimeters to feet, you just cube it. You just cube it. Take your grams to pounds, take your centimeters to feet. Put grams over cubic centimeter, right? You want units, you've got grams. Oh, no. Cubic centimeters in the bottom, right? Remember, if you write a number 0.714 grams over something, then you can put the 0.714 with the grams and put it all over cubic centimeter. Turn it into a fraction right off the bat. Do you understand that? Okay. Okay, when we write these, right? I mean, this is the thing. I mean, it's just oftentimes it's just one silly little thing that you can't see that doesn't allow you to solve the whole problem. If you take this right here, you've got to get this into a manageable fraction so that you can start canceling your units top and bottom, right? So this right here is the same as this. Do you see that? It's the exact same. It's like multiplying two fractions together. Multiply the tops, multiply the bottoms. There's your starting fraction, even though you don't have to necessarily write that one in. Okay? So once you start with this fraction, you can now convert your grams into pounds and your cubic centimeters into cubic feet. But you don't want to do something like this. Go 0.714 grams per cubic centimeter over 1. You don't want to do that. Okay? The units are already in a fraction form. And this number can be easily put in a fraction form if you simply put it over 1. Once you have two fractions, multiply numerators, multiply denominators. You should just run down and get here.
Use my book if you want, I don't need it.
What do you got? Yeah, we only got 1,000 in the other class, right? How we doing? Yes. Yeah. Yeah, you have to cube that number. Okay, so when we're going through, again, don't let these things get the best of you. Don't make up your mind right when you see it. Oh, I don't know how to do it because there's a cubed unit in there. Simply say, look, I'm going to follow what TJ told me to do. I'm going to go put this in a certain fraction form, and then I'm just going to start canceling out units and see where it takes me. So I'm going to start with this 0.714 grams per cubic centimeter. Now, I'm going to deal with the grams first because I'm more familiar with them, and I'll want to think about the cubic units in a minute anyway. So I got grams here, I want pounds. What am I going to take my grams to?
454.
There's a direct conversion, right? What is it?
1 pound is 454 grams.
Right. See how we make sure to have the number with the correct unit? We always have it in the top or the bottom, wherever it's going to be. Grams are gone. I have pounds now. Pounds per cubic centimeter. Sorry, that's not what we're asked for. We're asked for feet. So, do we have a conversion that will take centimeters to feet?
Yes.
Yes, we do. What is it?
30.48 centimeters.
30.48 centimeters in 1 foot. Unfortunately, this unit will not cancel with that unit. Right?
Right.
But if I could cancel this with that, right? I could cancel one of the units away. So with that in mind, if I put another one of these here and another one here, then I would have centimeter, centimeter, centimeter. That's centimeter cubed. That'll cancel. So all I have to do is cube this particular conversion factor. So I take 30.48 centimeters, 1 foot, times 30.48 centimeters over 1 foot, times 30.48 centimeters, 1 foot. There it is. 30.48 times 30.48 times 30.48. Don't know. 900 times 30, I don't know, 26, 5,000, 20, I don't know, 28,000. But centimeter times centimeter times centimeter gives me centimeter squared. 1 foot times 1 foot times 1 foot. Sorry, centimeter cubed, I mean. And 1 foot times 1 foot times 1 foot is 1 foot cubed. I now have my correct unit. Centimeters will cancel. What is that number? Does anybody have it?
The 30.48 cube?
What is it?
Are you wondering what the 30.48?
Yeah. What's a 30.48 cube?
28316.
28316.847.
0.846. Well, that's 84659.
That's good enough.
Okay.
847? Is that good?
Yeah.
That's what this equals. Centimeters are gone. All I have to do is do the math. How many significant digits? 3. So that will be what's our answer? 44 point what?
4, 5.
I got 5.
Oh, I have 4, 1. It's.
Because I cut this off maybe?
Oh, okay, yeah.
Because I use your cutoff, right? Okay. No, I still got 5. 44.5335. I'm going to go 3 significant digits, 44.5 pounds per cubic foot. Which one did you do?
I have it now. I must have just entered in the wrong number.
Okay. 44.5. So there's a lot we can do with this, a lot of different ways to ask the question, but the procedure for solving the question is always going to be the same. And I doubt you're going to see anything like this. Like I said, you're going to have a pretty straightforward one. convert, centimeters to yards, or, something that involved only one conversion factor, to it at the most. Okay? Questions? Okay. I'll bring my own book. Okay, a couple of more things. Density and specific heat. Okay, density. Density. When you talk about density, what you're talking about is a ratio of an object's mass to the volume that it occupies in space. And there's an algebraic expression, d equals m over v, where this is density, this is mass, and this is volume. Okay? I used to have kind of a hard time dealing with algebraic expressions because, after all, it's math, right? It's supposed to be math, but I don't see any numbers. All I see is letters, okay? Until I realized that algebraic expressions are relations between variables. And there's the word, they can vary. And only when we put in specific variables do we lock in that particular relationship to our situation. Okay? So, this is a relationship that we can use to apply to really an infinite number of possibilities. But we only have one equation, so I can only solve for one of those variables at a time, which means you have to be given the other two. So you have to be given two of the variables in order to use this equation. Now, typical units of density are grams per mil or grams per cubic centimeter. These are typical units. And it will tell you that 1 milliliter equals 1 cubic centimeter. cc. You ever hear that on the TV shows? Give him 32 cc's of epinephrine in his heart. He's going to die. cc is cubic centimeter. A cubic centimeter is nothing more than a cube. I should have taken that art class. My mom always wanted me to take. Okay? Horrible. Do it a different way. A cubic centimeter is just what it sounds like. It's a cube that measures 1 centimeter by 1 centimeter by 1 centimeter. It looks very similar almost to a sugar cube, or what a sugar cube would look like. If you take 1 mil, 1 cc out of a syringe, and you imagine a sugar cube that's been hollowed all out, a cubic centimeter, you could squirt that 1 mil right into that volume. So that's what a cubic centimeter is in terms of volume. Okay? So you can visualize that. It's equal to 1 mil. Therefore, if we look at this, since 1 mil equals 1 cubic centimeter, we can change these units without changing the value. Okay? For example, if you had a density what is that density, or what would that density be in grams per cubic centimeter? It's the same thing. It's the same value. Because if we do the unit analysis, we say 1.89 grams per mil, and we use our conversion, 1 mil is 1 cubic centimeter. Our milliliters cancel out, and we end up with grams per cubic centimeter. It's the same numerical value. You can just change the units. Sometimes that fact can be very valuable to you under certain circumstances. Okay? That can be very valuable to you. Everybody see? Okay, so our typical units, we have our algebraic expression. We know that we have to be able to solve this for all of these variables, provided that we're given the other two. So we have to be able to have D equals, M equals, and V equals, so that we can solve for each one of those individually, depending on what we're asked for on the exam or on the quiz or whatever we're doing. Well, there is a method, there's a way that you can, if you have a small foundation in math, you can derive those relationships. You can manipulate these variables so that you can solve for each one of them independently in terms of the remaining two. But there's another way to do it. I always remember the DMV. The DMV, right? DMV. And whatever you're asked to solve for, you cover it up. You cover that up in this expression. So if you're asked what is the density, you cover up D, and they give you the mass and volume, you divide it out. If they say calculate the volume, you cover up the V, and they give you mass and density, you divide the mass by the density. If they ask you for mass, you have to cover up the whole thing. It's density times volume, not 1 under it. Or not 1 over density times volume. Okay, that's the only little kind of kicker here. When you're asked for mass, it's density times volume. And you can clearly see that here. We multiply both sides by V to clear it out. M equals D times V. Okay? Does everybody see that? All right. So, let's do a couple of examples. I'll erase our typical units, but I'll keep our formula up there on the board. Let's calculate the density if 1.04 mils, I don't know if there's, I don't know how to spell occupancy. Wait, as a math, sorry. Oh. Calculate the density of a substance if 1.04 mils has a mass of 19.43 grams. So we come over here to our relationship, we cover up the D, and we have D equals M over V. So D equals M over V. I'm given a mass. How do I know what one of those is a mass?
Grams.
The grams, the unit's a dead giveaway, isn't it? The grams is a dead giveaway. So my mass is 19.43 grams. My volume is 1.04 mils. This is my density. Wow, that's pretty dense. 18.68269231 grams per mil. What's my answer? 18.7. Very good. Who said that? 18.7. Everybody see why? Yes? Everybody good? 18.7 grams per mil. What is this? What is that? I know it's a density, don't say that, I know. What else is it? Fundamentally, what is it? What is it?
Grams per centimeter cube.
Yeah, it's just still density though, right? But what is it? What is
It's
it?
the object as a whole, because grams is just the weight, volume is the size, but what we're looking at is actually what it is.
It's a ratio, yeah. But what's anything that has a different unit in the numerator than the denominator? It's a conversion factor, isn't it? It's not one that we're comfortable with or that we see usually, but it is, at its core, a conversion factor. Now, this particular conversion factor is very important. You know why? Because it converts between mass and volume. Look at all the other conversion factors that we have on our sheets. They're always converting between different units of length or different units of mass. You know, 1 foot is 12 inches. These are both units of length. Rarely do you get a conversion factor that allows you to jump between one unit and an entirely different type of unit. Density is one of those things. It's one of those units. Okay? Bless you. We'll do an example of each one. Calculate the mass, let's say in grams. This time we're given density and volume, and we want to know mass. No calculator? Great. Everybody got an answer? What's our answer? Anyone with a calculator got an answer?
396.
396?
Grams per million.
Let's see. I got 396 grams. What is it?
Grams per mil.
Well, let's see. We want to know the mass, so I'm going to cover up M and get D times V, right? So mass equals D times V. My density is given as 1.05 grams per milliliter. See how I made that into a fraction? I got my units in a fraction here. I just put this over 1. So I put that in a fraction so it could be usable. and my volume is 377.0 milliliters. Milliliters cancel, leaving me with a unit of mass, coincidentally. So, I think the number sounded right, I just didn't like the units.
Yeah, it should just be grams because it's,
There you go.
gas.
I got an answer of 395.85 grams. Significant digits? 3. Three? Why?
Because you don't think there's one? Oh, we could. Supposed to be 4.
Everybody, I can see everybody else and say, well, why isn't it 3? I can see the look in their eyes. This is
Conversion.
Do you think it's 4? 3? What is this?
The conversion.
It's a conversion factor, right? Do you really think the density of this solution is 1.05? Or could it be 1.051176517112, whatever, or 1.48, whatever? It can be more than that. So it's got to be the 4 digits. So that's 395.9 grams. And I noticed that that's wrong in here. So be careful. Things are wrong. You know, don't be so, focused on what's written there. You just take it blindly to be right. Okay. The density of rubbing alcohol is 0.786 grams per mil. Calculate the volume so in milliliters. Containing 32.0 grams. What do we have? .7 gallons? Milliliters. Right. Everybody getting those? Yeah? See how we're using this? Let's see, calculate the volume, cover up volume, we got mass divided by density. Volume equals mass divided by density. Our mass is 32.0 grams. Our density is 0.786 grams per mil. This fraction, when you divide by fraction, you invert and multiply, right? So this will put grams on the bottom, which will cancel it. These are gone. And we get 40.7 mils to 3 significant digits. I think that's it. Yeah, 40.7124, whatever. Did you make another error?
No.
Yes, you did, didn't you?
I just added a 0 to one of the numbers.
Sure. Why not? Make it more accurate. Well, okay, this is really, kind of the only way that you'll see the density problems. Now, there is another variation where the volume, you calculate the volume of regular solids, okay, given a measurement of the rectangle or whatever it may be. We can do one of those real quick. Let's do one, just so you have a working example. It's in the homework. Yes, it is. It's copper. It has to deal with copper. So if we take a look at these, you don't necessarily have to give you the volume. We can give you a regularly shaped object and then give you the measurements around, for example, a cube or a rectangle or what have you. Then you use algebra to determine the volume. So one of the homework questions says, density of copper, and that's, we might as well start using symbols for the elements, right? Cu is the symbol for copper, is 8.96 grams per cubic centimeter. Now, whenever you see your densities given in grams per cubic centimeter, this is almost automatically your tip-off that you're going to have to use some type of algebraic expression to calculate the volume of a solid. Otherwise, it would be in grams per mil. Let's see. Calculate the mass. .3 centimeters by 3.1 centimeters by 8.0 centimeters. Now this one is just a little variation. There's no need to freak out. We're given the density and we're asked for mass. So we come over here, we cover up our mass, and we know that our algebraic expression is mass equals density times volume. Right? We're given the density. We're given the density, but I don't see any volume up there, do you? I don't. But I do see a rectangle, and I see the measurements, length times width times height. Doesn't matter which one is which. So I know that my volume of a rectangle equals length times width times height. Okay? And if you didn't know that, you could simply Google or look online at what's the volume of a rectangle. Or open up your math book. Or take a look at your homework assignment last week from math. would be in there last semester. So I'm going to put these numbers in. Notice that in addition to multiplying the numbers, I have to multiply the centimeter times the centimeter times the centimeter. .04 cubic centimeters, round number. Now, you look at this and you say, look, we're multiplying 2 significant digits, 2 significant digits, 2 significant digits. You don't round this to 2 significant digits. When you round, you only round one time, and it's at the end when you report your final answer. If you round this number, and then you use that again against the number that you rounded, and then another number that you rounded, you're going to get further and further off, because error is not linear. Error propagates exponentially. Okay? Which means if you take a number that's off by 10%, and you multiply it by a number off by 10%, you do not get a result that's off by 20%. It's actually more than that, because it's not linear in nature. Okay? So, I put this in here, and we have 8.96. I'm going to put my density as grams per cubic centimeter. I'm going to put that in a fraction form. And now I have 57.04 cubic centimeters over 1. What a coincidence, my cubic centimeters happen to cancel out, and I am left with grams, a unit of mass. Is that my answer? No. What's my answer? 511?
Grams.
She's still shaking. No. What is it?
That's what I'm stuck on, but that's not 511.
What is
Can you
it?
put it into scientific notation?
You could, but you don't have to. How many significant digits do we have to have, first of all? 2, right? 2. This is a conversion factor again, so we have 2. So I need to round this to 2 digits. What? Yeah. Here's my second digit right there. I was going to say the 1, but luck would have it, there are 2 1s. So I can write this 510 grams, which is 2 significant digits, or I can simply go 5.1 times 10 to the second grams. Either one of those is going to work. Unless the problem, which I didn't read, says express it in scientific notation. It does not. It doesn't say we have an option, so either one of those answers is accepted. Okay? You good with that? You're looking at me funny.
Me?
No.
Since it's 2 significant digits, wouldn't it just be the 5 and the 1?
Well,
Or is it-
yeah, but you have to maintain the same approximate value, right? You can't take 510 and round it to 51.
Okay.
It's got to be about the same value.
So the 1 gets taken off and turns into a 0, so it's...
A non-significant 0, yeah.
Okay.
So the value, just remember, every time you round a number, okay, when you finish rounding, take a second, take a quick look and say, are these approximately the same values? Because rounding a value, rounding a number should not change a complete order of magnitude. You shouldn't go from 100 to 50. Or, something with times 10 to the second to 10 to the 1, You wouldn't round, something that's 40,000 and round it to 4,000. Okay, so just take a quick look and say, yes, I'm at 511, I rounded to 510, these are close. Again, it's multiple choice, so you're going to be picking these numbers out. You can't have this. Can't have a 0 after it, because then there's 3 significant digits, right? Atlantic Pacific method. Okay? So you have some other, we good?
You're good.
Okay. We have some other examples of that in the homework, where you have different regularly shaped objects. I just wanted you to have a template. You're more than likely going to have to jump online or go to some math resource to get the volume or the algebraic expression used to calculate the volume of those regular solids. Okay? In lab, we're going to actually do something like this, where we are going to measure a regularly shaped object, and then we're actually going to put an irregularly shaped object into water and get its displacement. And it's going to drop something in water, and it's going to push the water up. And the amount that the water displaces is equal to the volume of the irregular solid, because you can't measure it. Okay, we all set? All right. Last thing. The last topic that we're going to discuss today is heat capacity. Heat capacity. Now, heat capacity is also represented by, oh, you know what? One thing. With respect to our density, there is a relationship the ratio of the density of a substance to the density of water is called its specific gravity. So specific gravity, and there's not a whole lot to do with this, is going to be equal to the density of the substance divided by the density of water. This is our specific gravity, right? And what specific gravity is it's the density without the units. Okay? So if we were to look at, because the density of water is taken as 1 gram per mil. It does vary with temperature, and there's a table. It varies slightly with temperature, but generally we take the density of water as 1 gram per mil. So if we were to calculate the specific gravity of a particular substance, of a substance that has, let's say, let's say that we wanted to know the specific gravity of a substance that had a density of 0.914 grams per mil. The specific gravity is simply equal to the density without the units. It's the same number. Because the ratio of the density of substance to the density of water Water's 1, all it effectively does, the density of water, all that does is cancel out the units. Okay? So we would have something that looks like this. Would equal the density of the substance divided by the density of H2O, which in this case would equal 0.914 grams per mil over 1 gram per mil. Units are canceled, and you effectively have the same value, just without the units. Okay? The only kinds of questions you can see on specific gravity have to do, with what I just said. If you have a specific gravity, you say, hey, what's the density of a substance with a specific gravity of 0.914? You simply put the grams per mil on that to get the density. And if you're given the density and you want to know specific gravity, you just take the units off. It's the same value. Okay, it's the exact same value. Pretty straightforward. Okay. Everybody good? Almost forgot that. Okay. Now the heat capacity, did you need that up there? No, I thought I heard something. The heat capacity is also an algebraic expression. And it's Q equals M times specific heat times delta T. This is a Greek delta. It's a capital D in the Greek alphabet. And it's a term frequently encountered in thermodynamics. It's an area of chemistry that deals with heat and energy exchanges during chemical reactions. That's where I mostly ran into it. I saw it some in differential equations, but mostly it was in my thermo class. And you can interpret it as change in. So delta T would be change in temperature. Now whenever you see the delta, whatever the symbol is, it's always final minus initial. If you saw delta P, it would be the final pressure minus the initial pressure. Delta T, final temperature minus the initial temperature. Okay? This is mass. This is, first of all, this is heat. It's heat, or energy. Okay? All heat is energy, but not all energy is heat, because you have other forms of energy, potential energy, chemical energy, all kinds of things. But this is heat, this is mass, and this is specific heat. Anybody know what specific heat is? Anybody ever heard of that term? Specific heat. The specific heat is the amount of heat energy, right? I'm going to say energy, and then I'm going to specify that it's heat. It's the amount of energy required to raise 1 gram of a substance (1°C). It's the amount of energy or heat that you must supply to 1 gram of a substance to raise that substance 1°C. The specific heat of water 1 calorie. Or alternatively, 4.184 joules. This is a new unit for us, joules, but it is on our periodic table as a unit of energy. 1 calorie is 4.184 joules. This one looks ugly, doesn't it? This one looks like a lot of work. But everything is basically the same as what we saw in our density formula. Namely, we have all of these variables, but the bottom line is that we have to be given all of those variables because we can only solve for one of them at a time. So all the other ones we have to be given. We have to be given those. Okay, so let's run one calculator. Now, if we look at this formula, let's just kind of take a minute and say, okay, here's the heat. The amount of heat that we have to put into a certain substance depends on how much of the substance we have, how much we want to raise the temperature, okay? How much of the substance. I have to put more heat into the lake to raise it 1 degree Celsius than I would a glass of water, right? So it depends on mass, it depends on the specific heat, how much energy do I have to put into the substance to raise it 1 degree Celsius, or 1 gram 1 degree Celsius, and then what's my temperature range, okay? Now heat, there's no such thing as negative heat, right? There's no such thing as negative energy, right? Man, it's negative energy, man, right? There's no such thing as that. Negative signs are something that we've come up with to indicate the flow of the heat. Is it coming into the system or is it going out of the system? Okay? So if we look at our equation here, the sign of heat, let's see where that comes from. Is it positive or is it negative? Is it coming out of the system or is it going into the system? Going into the system, going out of the system. Can we have a negative mass? Have you ever heard of anything that has a negative mass? No. I've never heard of anything that has a negative mass. Have you ever heard of an object that when you put heat in it, when you add heat to it, the temperature goes down? Have you ever heard of anything that you heat up and the temperature goes down? No. So you can't have a negative specific heat either. Can you have a negative delta T? T final minus T initial. Yeah. Let's say you're heating an object. Okay? By definition, when you heat an object, the final temperature is greater than the initial temperature. Right? Otherwise, you're not heating it. Right? The final temperature has to be greater than the initial temperature in order to be heating, by our definition. If the final temperature is greater than the initial temperature, then delta T will always be positive because the final temperature is bigger than the initial, right? Which means Q will be positive because this has to be positive, this has to be positive. Now let's say you're cooling an object. By definition, if you're cooling an object, the final temperature is lower than the initial temperature, right? Otherwise, you're not cooling it. If the final temperature is lower, smaller than the initial temperature, delta T will always be negative, right? So when an object is cooling, we have a negative Q. The heat is leaving the system, right? When an object is heating, Q is positive, energy's coming into the system. These are just sign conventions for us, okay? A negative 400 joules will burn you. So will 400 joules. There's no such thing as negative energy. A negative sign just indicates that the energy is leaving the system. Everybody understand? Okay? Positive and negative Qs. Okay. Let's see. Now, you have to take a little bit of time and you have to think about how to solve these because you have to identify the variables. You have to identify the numbers that go in the particular positions. And the units are going to be a huge help for you under these circumstances. So here's our question. .0 Notice those funny units on specific heat. Calories per gram degrees Celsius. Look where your specific heat is, right here. Okay? Your specific heat is going to multiply times mass, which means it's got to have a unit of mass in the denominator to cancel. It's going to multiply by temperature, which means it's got to have a unit of temperature in the bottom to cancel. And if you divide it, it's got to be able to cancel out a unit of heat or energy, which in this case is calories. So we have Q equals M times specific heat times delta T. Over here we'll solve for our delta T first, which is T final minus T initial. I go back and I read. The sample was initially at 78, it's dropped in, blah, blah, blah. It's cooled to 17. Do you see which one's T final and which one's T initial? Right. So T final, 17.0 degrees Celsius. Our initial, 78.0 degrees Celsius. That gives us a delta T of what's the delta T? Yes, very good. It's negative 61.0 degrees Celsius. Do you see it's important to carry that zero? Remember, we're subtracting here. So adding and subtracting, we do not look at significant digits. We line up the decimals and we subtract them. So this was 17.0 minus 78.0. We have to keep that 0.0. That's important because it keeps this at 3 significant digits when we go to plug it in. Okay? So now our mass is 50.00 grams. I'm going to put that over 1 so I can show you how the units all cancel. This is 0.108 calories per gram degrees Celsius. And my delta T is negative 61.0 degrees Celsius. Look at this. And I'm left with calories. What a coincidence that that's a unit of heat. Calories or joules. It's a unit of energy. We use it. $50 times 0.108 times negative 61. What do you get? Sign? Yep. Negative 329.4 unit calories. Very good. Is that the unit or the answer I'm going to report? No? What do I need?
It has to be 3.
Yep.
So negative 329 calories.
Okay? So if you really look at this problem, okay, it really would depend on it's a multiple choice exam, so you're going to take a close look at what your possible answers are. Because the question is asking us, calculate the heat released. It's already telling us that it's negative. So the heat released is 329 calories. That would be your answer. But if it just said calculate the heat, then you want to put the negative sign in there. Both of them are going to be equally correct. I just don't want you to be thrown off by the possible answers here. Very technically, from a very technical nature, calculate the heat released. The answer is 329 calories. If you want to calculate the heat, then it would be negative 329. It is released because it's cooling. Okay? Just a splitting hairs there, but it's true. Okay? Everybody good?